Okay, let's begin. So first of all, I would like to summarize the results and facts about the algebra A of regular functions. So I recall my notation. A, the algebra of regular functions on the set of Young diagrams. So the definitions are as follows. So we have this algebra. One can say in the center of a picture. And then this algebra appears in different ways. One way is to represent it as an isomorphic image of the algebra of shifted symmetric functions. So all of these arrows are algebra isomorphisms. So let's denote it symbolically by 1. And next, we also have some other isomorphism with the algebra of symmetric functions. Let's denote it, this arrow by 2. But here we identify the algebra of symmetric functions and the algebra of supersymmetric functions. And I will recall this notation. And next we have another arrow, now say number 3, from another copy of the algebra of symmetric functions, but in a different way. So we take again the algebra of symmetric functions, but take its quotient by the ideal generated by P1, the first power sum. This is arrow number 3, and maybe there is also some arrow number 4, and here maybe I will write the object as the corresponding object as the algebra of polynomials in infinitely very many variables, denoted as pi 0, pi 1, pi 2, and so on. And all these arrows, I recall, are algebra isomorphisms. And what is arrow 1? Arrow 1 appears when we take functions on the Young diagrams, take functions on the row coordinates of Young diagrams where f, say f1. f1 is an arbitrary shifted symmetric functions. And next, the arrow 2 appears if you take the supersymmetric realization of the algebra of symmetric functions and take as arguments the modified Frobenius coordinates. So we take f2 of lambda by function Young diagrams, which is by definition a supersymmetric function in the modified Frobenius coordinates. These are modified Frobenius coordinates. So these are modified Frobenius coordinates of lambda. And what next? And what next is, given a function f3, an element of the algebra of symmetric functions, we assign to it, sorry, this is f number 3, we assign it a supersymmetric function. So this is by definition a supersymmetric function in my notation, which are curve interlacing coordinates. So in the conventional notation, we don't use the minus sign, but in my notation, it corresponds to taking the minus sign. And finally, the arrow number 4 just means that we realize a polynomial, maybe it's better to write, just realize it's better to write a bit differently. So given this abstract element, we assign a function, on a Young diagram, which is by definition the sum of all boxes of our diagrams. We then take the content of a box and raise it to power k. So k is 0, 1, and so on. Okay, and all these arrows are different realizations of this algebra A, and maybe I should also recall that here in the first picture we can also take the value at the column coordinates, and this will correspond to some involution here or involution here. So this realization is compatible with transposition of a Young diagram as an argument here. Okay. What next? And some important example I recall. Example of a regular function is obtained as follows. We assume that lambda has n boxes and mu has m boxes, and m is smaller than n. Otherwise, the result will be 0. And we take the following expression raised to the following factorial power. This is a simple number factor. Take this quantity, which I recall is the number of standard Young tableau of a skew-shaped lambda over mu or 0 if mu is not contained in lambda, divided by dim lambda, and maybe it's better to put here with symbol indicating that it's equal to 1 if mu is contained, 0 otherwise. Okay, this is a more precise notation. And the result, it turns out that the result as a function of lambda, and mu is a parameter, an index, then the result is some element of algebra of shifted symmetric functions, and hence this is an element of our algebra A. And the definition I recall of this object is similar to the construction of ordinary Schur functions, the same procedure, first taking finitely many arguments, then pass to a limit using some stability property. And this is a very important result, as I will repeat again and again. What next? One more example is as follows. Maybe I would like to repeat one more remark. Then in the algebra of shifted symmetric functions, because we have some nice analog of sure functions, we also have analogs of H functions, I mean complete homogeneous functions, an analog of them, which corresponds to one row mu, and analog of elementary functions, which correspond to one column diagrams, but we don't have a canonical analog of a power sum function. So instead, there are various versions which are convenient to some of our situations. So I recall that one possibility is to take one version, or maybe it's better to say, right, an analog K is the function PKC of lambda, which is defined as the sum we take lambda sub I minus I plus C. C is a free parameter. We raise to power K and subtract with making the result correctly defined. So this is one possible analog of a power sum, but there are other. And one different analog is the following. So I want to define another object, which is denoted as follows. And it is defined as by analogy, strict analogy with this one. Namely, no, maybe I will write a bit differently, sorry. So I want to, maybe I will, sample a function is defined as follows. So assume that rho is a partition of some size, again, M. And I want to define it as follows. Same factor. Next, I take actually the character and I will explain what this means and divide by the dimension. So what is written here? I assume here that otherwise 0. So I assume that n is great. Oh, sorry. So I assume that n is greater than m. So I need to put here some partition of the same size. So I add 1, 1, 1. Okay, and this corresponds in terms of characters. If you adopt the realization of this quantity as symmetric group characters, this means the following: when we embed the symmetric group of degree m to the symmetric group of degree n in a natural way. Okay, so we take some element. Here with the cyclic structure given by rho, and when we regard it as an element in the larger group, and this amounts to say that we add 1, 1, 1. Okay, so the claim is that it is again element of this object, this algebra of regular functions, or it is, in other words, it is shifted symmetric functions. Why? This is easy to see because we have a following relation. Actually, we have, so this, it is simply a linear combination over diagrams of the same size m, and here we take these characters, okay, and multiply it by, so this is, I would like to see. What is the meaning of this? So we assume that m is fixed. It's, one can say this some small number, but we want to vary lambda. So this is simply some index. And because m is fixed, we assume that we know something about these coefficients. Okay. And because of this relation, we can say what are these more complicated objects. Okay. So this is one, and this is easy to see. If you wish, is some exercise. Okay. So after all this, I would like to begin something new. Namely, I recall some identities. So the subject can be titled as follows: growth, maybe it's better to say Plancherel growth of young diagrams. So this is the subject I want to discuss now. I recall the identity for any n. We have the identity, the sum of squared dimensions divided by n factorial is equal 1. So this was one of the problems, and I recall its possible proof, perhaps the simplest one. So the proof is as follows. we write the identity. Okay, and then apply to both sides of this equality, then apply, we call it Plancherel specialization. Plancherel specialization, which is as follows: P1 goes to 1 and Pk goes to 0 for all other k. And under this specialization, we get on the left, we get 1. This is one factor here. And the remaining factor appears from this, because we know that the specialization under this procedure gives us exactly simply dimension divided by n factorial. So this is a proof. But of course, we know, I think that you know that this expresses the facts that the sum of squared dimensions of irreducible representations of a finite group equals its order. The order is this one. So this is a manifestation of this equality from representation theory of a symmetric group. But here we have a purely combinatorial, independent of any representation theory argument. Okay. So this is one. Another important identity is the following. So assume that lambda is again here. And we have an identity that the sum of a nu which are over lambda, that is can be obtained by adding a single box, dim nu divided by n plus 1 dim lambda, again equals 1. Okay, and this is also, this can be proved. This was one of the problems. Some people solved it, and some people did not. But actually, it can be solved in almost exactly the same way as here. Only we start with a little bit different identity. Instead of this one, instead of this one, we begin with another identity, which is as follows. Namely, we write as lambda multiplied by P1 is equal to the sum, just the same sum, we know this is the simplest version of the Pierre rule. And next we look at this and apply the same Plancherel specialization. And because we know that under this specialization, lambda goes to lambda divided by this size factorial. Okay, so applying this specialization, we apply it to this diagram. Here we get 1, and here a similar expression. We immediately get this one. So this is an easy proof. Okay, one can prove it in different ways, but this, I think, is the simplest one, provided we know this result. Okay. But now look at these two identities, this one and this one. In either case, we have one on the right and a sum of positive numbers on the left. And once we have such effect, such identity, it's tempting to interpret these summands on the left as probabilities. So what then we obtain here? For the first identity, maybe it's better to introduce some. Write this as relation 1, and this one is relation 2, just for reference. So interpretation, probabilistic interpretation of 1 and 2. So 1, what is this? So this is the so-called Plancherel measure. Plancherel measure on the set of Young diagrams of a fixed size n for each n. So we get some measure m, and the weight it assigns to a given diagrams is so we get a probability measure, which is called Plancherel measure. These terms was suggested by Anatoly Moiseyevich Vershik, and it is a common term now adopted by all people. Actually, it's not in accordance with the terminology in representation theory, because from the point of view of representation theory, one would take the dimension only here, not square dimensions. And but nevertheless, this is a common term now, so let's use it. What about 2? About 2. So let's introduce some notation. I want some notation for the set of boxes which can be added to a given Young diagram. So given Young diagram of arbitrary size, say n. I need some notation, so let's write as follows. Boxes up, lambda. This is boxes that can be appended or added to lambda. So there are finitely many boxes which we can add, and this is the set. And 2 so identity 2, I recall it. So here we look at this new. So new is obtained as follows. We add some box, and this box is from this set. So we get a probability measure on this set. So by definition, let's denote it as follows. With index lambda, the weight is equal to dimension of lambda with this box edit and for any box which is in this set. So we get a probability measure. It's called the transition measure of a given Young diagram lambda. I think should be attributed to curve. I recall the picture which corresponds to curve interlacing coordinates. Picture. His idea was to look at this broken line, the boundary of a Young diagram, and assign to each corner, to each point, which is on a corner, inner or outer, some number which is the content of simply the difference between the j coordinate or the column coordinate and the I coordinate, the row coordinate. So actually we can have in mind this picture. So such a picture. So we have with quarter plane, and given a point, we draw the diagonal and the line which is parallel to it, and take this coordinate. We assume that we put the real axis here in such a way. Okay, so we have 0, 1, 2, minus 1, minus 2, and so on. So this is our real axis only in this broken form. Okay? So, and then the content is just the image of this projection. Okay? And now what is important to notice in connection with the curve diagram? So this point is x1, okay? And this point, so this, maybe this length is x1 minus y1. And this one is, so this point corresponds to this, maybe this is a bad color. And so on. And so this length, blue, is this one. And this length, red, is, and so on. So, okay. And the boxes which can be added just correspond to the x points. So we have the bijection boxes up lambda are in bijections with this set of inner corner which I want to identify with the care of coordinates. Okay? So my aim now is, so I want my aim is compute the transition probabilities, transition measure. I will call it also transition probability for some reasons which will appear. Transition probability. I regard this, okay, so not transition probability, the weights. Of the measure, this measure, in terms of a care of coordinates. How to do this? The idea is follows. So given some lemma, so assume that we have interlacing sequences, x's and y's, and here these are not care of coordinates for a moment by just arbitrary real numbers. So these are arbitrary real numbers. And take the product. And u is some formal parameter, complex variable. It's better to say complex variable. So we take this rational function in variable u. And take its expansion on partial fractions. It's possible because we assume that the x's are pairwise distinct. So this object, this real function has simple poles, and so it can be written as the sum over k ranging from 1 to r, and u minus x k. And here we have some quantities, some coefficients which appear. Let's denote them as okay, so pk. Okay. And the claim is as follows. First, the pk are strictly positive, and next their sum r is equal to 1. And actually conversely, so assume that we have some numbers, x and y's, and write this expansion on partial fractions, then these conditions are equivalent to the fact that these numbers interlace. This is a beautiful fact. How to prove it? It's not difficult. Okay, so what is pk? Let's prove it in one side, just as I wrote here. Why are they positive, and why the sum is equal to 1? So why they are positive? But it's simply because we can compute these coefficients, these quantities. These quantities can be computed by taking the residues. Okay. So what is the residue? So pk, proof. The pk, given k, these coefficients is the residue of our expression in u equal to xk, and hence it's equal to the product over I from 1 to r xk minus y. Well, maybe, sorry, I changed to change. And divided by the product of xk minus xi, and I is distinct from k. And looking a bit closer to this expression, we see that from our condition, this one, we have here exactly the same number of positive and negative factor in the numerator and denominator, and thus this quantity is positive. And how to conclude this? This is just by looking at the limit of the asymptotic of this expression as so why the sum to 1. Just look asymptotic as u goes to infinity. The left-hand side is this one, and so the right-hand side should be of the same order, of the same asymptotics, and this gives us this relation. Okay. And now my claim, this is a theorem. Theorem curve. I think it's we can guess the result. Okay, so just write for the box in the set corresponding to xk. Then we have this transition measure corresponding to this box, which is by definition, I recall it again, dimension of lambda So this is the definition, it's not the claim. It's not the claim, but the claim it is this quantity. From this identity. So these numbers are taken from this expression. I want to prove this result. Proof is as follows. We need some expression for the dimension. The relevant expression is the Hooke formula. I recall the Hooke formula. To recall the Hooke formula. It was in lecture 6, and it claims as follows, that we take the dimension divided by this. This is equal to the product of the Hooke length of the boxes in our diagram. Okay. So what we need, maybe I need to write it in a more detailed way, to emphasize that the hooks are taken in a given diagram lambda. Okay. So what we need to prove then, we need to prove that so consider the picture. Okay. So we have some picture like this, and this is our box. Our box, which is added to our diagrams. Let's highlight it. This is the red box. So the quantity that we need from the Hooke formula, it's the same as the product of the okay. So nu, in my notation, nu is the bigger diagram. Okay. So this factor disappear on the right-hand side because the Hooke product is already corresponds to normalization of a dimension. Okay, so we need to prove this formula. But let's compare the Hooke length in the smaller diagram and in the larger diagrams. What happens? The boxes are all the same, except this one. This is a new box which appears in the diagram nu, but its contribution is 1 because the Hooke length is 1. So actually, what we have And the next observation is as follows. So look at this row and this column. Okay. So assume this is row number I and the column number j. Okay. In all boxes, so I will write it in words. In all boxes outside the blue region. So for all boxes here, 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 the hook length, in lambda and with respect to nu are the same. So nothing happens after we add this box. If you take this hook, it does not affect this hook. So the product, actually, we can cancel this hook length and look only on the hooks which corresponds to these boxes, this one. Okay. So actually it suffices to look at the boxes, at the contribution from the boxes in this row and this column.
Excuse me, didn't we forget n+1 in the right fraction?
The factor n+1 on the right does not appear.
Yes, I see.
Appeared because of its normalization. Okay, because okay.
Yes, I see.
Is it okay, Timur?
Yes, I understand. Thank you.
So this is our box. Okay. So actually, the right-hand side is as follows. We take the product of the blue boxes. These are blue boxes. And what we have to take? We take simply this hook length, okay, and divide it by this quantity. Because in the new diagram, we have just to add 1 to take account of these new boxes, of his new box which is added. So we only have to look at this expression where the product is taken on the boxes here or on the boxes here. So let's examine first the boxes on this horizontal strip. So examine the product over blue boxes, over the blue boxes. The blue boxes in the ith row. Okay. So what happens here? Again, look at this picture. Maybe I will write it in. I want to zoom in. So we have something like this. So this is our point, and this is our blue region. This is our region. And this is, don't forget, this is xk. And this is so look first at this box. And don't forget what we have here. This one. So this hook length is xk minus yk, okay? Because this is just the height, this is just the height of this column. So the contribution from it is xk minus +1. Okay. But move on the left and look at this position, what happens here. And then we see that what happens here, that we have xk, sorry, minus, because the hook length is a bit greater. We add 1 and divided by this quantity +2 and so on until we move up to this position. But then this factor which will cancel, and the result, and this will produce us because of this point, this will produce us this expression. And as long we move on the left, this picture will repeat and repeat. So the final result will be as follows: xk minus so on, xk, the final possible value. And here we have xk minus So we have as many factors in the numerator and in the denominator. And just the same picture, just the same, just the same for the blue column. This one. So we just one can see that we regard this picture transposed, and we get exactly similar expressions, only the y's and x's we have different pictures, so a little bit different. The difference is that here we get positive factors. And again, the products involving xk in a little bit different way. And again, you have the same number of factors here and here. So we combine these two expressions and we get exactly what we want. We get exactly what you want, this. And this also shows that this quantities is indeed positive. If you wish, we rearrange it a little bit. So this is a very nice expression. Why it is very nice? Because by the very definition, the care of coordinates are something which is which looks quite natural from the point of view of adding and removing boxes. And this result has consequences, which maybe I will try to explain them later. But I think that the result is very nice, quite. I don't know if it's possible to find a good formula for the dimension in terms of the care of coordinates. I don't know, I did not see it, and perhaps it does not exist a good expression, otherwise Kerr found it probably. So I don't know, I didn't think about it. It seems probably it's difficult, maybe one can try. I don't know. Today I would like to just stop at this moment. The reason is that I would attend some lecture. Maybe you are also a bit tired, but let's stop at this moment. And tomorrow I will send you some problems related to this stuff. So, bye.
Thank you. Goodbye.